the premise of this talk is that a number of people do not think that software vulnerabilities are present on a mainframe. This is untrue, and hopefully I'll show it later. But there's also the type of testing that's currently happening isn't equipped to find these type of software vulnerabilities. So either you have an auditor who just doesn't look at these types of things, like they won't test software like this, or you have a pen tester, and there's a good chance that they don't even, if they don't have, I guess, more knowledge on a mainframe, they won't know about how to find these vulnerabilities. So a little something about me. I'm Jake Labelle, and around about the start of the pandemic, I got fairly bored and decided I'm going to learn how to hack mainframes. And so I started skilling up, and in the past 6 months, I found more than 10 0 days, but yeah, around about 15 now, I think. And also, IBM Z security people follow my Twitter, so I think that's kind of funny. So they'll sometimes message me after I say, "Oh, I found another one," and they'll go, "Oh, when are you going to write the report?" So yeah. So I guess, yeah, the first thing that, if you know anyone who is a mainframer, they'll tell you mainframes are unhackable. Hopefully, yeah, this is patently untrue because I've found a number of them, and they're 0 days, so this means that they're vulnerabilities before the manufacturer found it, so not good on their side. And mostly, and also when I say manufacturer, I'm talking about IBM because that's the only binaries that I've really looked at for mainframes. Most of the vulnerabilities are LPEs, or local privilege escalation. So what this means is that from any user on the mainframe, if I have any user, I can escalate the privileges up to special. And there's also been a couple RCEs, remote code execution, and this is a vulnerability. So if I have network access to a mainframe and they haven't patched this one vulnerability I found, I can gain special just from that. And so all of these have been reported to IBM that I found. And one thing that makes people think mainframes are unhackable is they go on the CVE site and they go, "Oh, there's no CVEs there." But the reason why this is the case is not because there's been no vulnerabilities found, it's because IBM Z doesn't do CVEs, so that's why you don't find them. And also, if you want to see some of these findings, if you have access to the security portal where they do release their vulnerabilities, you can see that, for example, there's a 10 CVS score that I found recently. I guess, and then the other question to people who've never heard about mainframes will go, but who actually uses mainframes anymore? Why do we care about this? And this is, again, untrue. Most of the largest companies in the world use mainframes, and that if you do any sort of credit card transactions, which everyone does, it's probably handled by a mainframe. And also, each one mainframe can handle a large amount of transactions. So even if your company only has like 1 or 2, it's probably doing things that are quite important. So I guess the first thing is, what makes ZOS and Windows or Linux different? And again, this talk is only going to be about ZOS because it's the main mainframe that most people use. It's the one that that IBM creates. And so there are one of the biggest differences is that Windows or Linux, you run a program, and that's how everything works. In ZOS, you submit batch jobs with JCL, and these are submitted to the system, and then at some point the computer runs it. And in the olden days, you'd get like a line printer that would tell you, "Oh, your job's completed," but nowadays it's all emulated. Another big difference is that in ZOS you have data sets instead of files. For this talk, there isn't really much. It's not really relevant, but it's something to keep in mind that files and data sets are different. And then for this talk, something that is quite important is that RACF, which is IBM's external security manager, which is what you'll find on most ZOS. And the way it works is that all security is done through it. So whereas on Windows and Linux, you might have like your web app security, and that will be in one place. And then you'll have your database security, and that will be another place. And you might have like your host security, and that will be another place. on mainframes, everything is just handled by one external security manager called RACF. So if you want to see if you can read a table, read a table in DB2, you would just look at RACF, search if you have read access on that table profile, and that's how you would access it. If you want to see if you can, if you want to see your user privileges, you'd look at RACF. And one of the things that's important about RACF is that there's a authority called special that users can have. Special is, you can think of it like root on Unix, where the way special works is that if you have special, anytime you access anything, when it checks RACF, it will say you can access it. So if an attacker had special on your mainframe, it's game over, and that's bad. And then the last thing that makes it quite different, but only when you're doing this type of software exploit dev type stuff, is that it runs on its own architecture called zarch, so it's not like x86. So if you want to know how to hack a mainframe in this way, you need to know its special assembly instructions and stuff like that. And also that programs are compiled in a way called language environment normally, and so you need to understand how language environment works to hack a mainframe. So why would an attacker decide to target a mainframe? And there's some good reasons why they would try to do it. And first off, one mainframe handles hundreds of services. So whereas on an attacker might need to pop hundreds of Windows boxes and Unix boxes to get access to all the data in the bank or something, if they just hack one mainframe and get special on it, then if anyone who runs a mainframe they know or handles mainframe services, you know how much damage they could do with that. Also, the amount of transactions and data that flow through a mainframe, if someone was able to gain access to it, they could be changing stuff, they could be deleting stuff, and yeah, so a lot of problem there. Another reason why they would target it is that the type of places that run mainframes are big companies like banks or governments. So these places just, I guess, by default hold a lot of sensitive data. So they might want that type of stuff. Also, I guess normally some of the ways that you get a foothold on a system is you compromise one user, but mainframes typically have one mainframe will have thousands of users, so there might be more opportunities to get a foothold on the system. And lastly, seemingly no one else is, so you might, whereas in the past two talks they talked about all the detection they're doing on Windows and stuff, it's there's less detection. So saying all that, why don't we hear in the news about this bank got hacked on their mainframe or that type of stuff? So I guess the first reason why is that ZOS and Z architecture is quite weird. So you aren't typically a normal hacker or a normal pen tester doesn't know much or anything about ZOS, let alone Z architecture. Also, another thing that makes this kind of hard to learn is that a random pen tester or a random criminal isn't likely to have access to ZOS to test different exploits. This doesn't stop like a nation-state attacker. They can get access, but it will stop just a random person. There's also relatively little hacking information out there, so if you want to learn how to hack a mainframe, it's basically go read their 200-page documentation about how mainframes work, and there's that, or there's one or two, there's a couple talks in Black Hat and DEF CON type stuff. Another big problem is that most security is done by audit. So if you ask someone, what security, how would you test the security on a mainframe? They're probably going to tell you something about, well, you look at this RACF profile and you test this and this and this. But it's kind of hard to find the type of people who you could ask about this type of security. It's important security to do, but it's just not this type of exploit dev. And the last reason is that the type of tooling for hacking on a mainframe is incredibly limited. There's no IDA, and the type of debuggers you can use are very primitive, probably is the best way to say them. So that's quite difficult. And for example, you'll have lots of fuzzing ability on Windows or Linux, but I have to write my own fuzzing tools to test the mainframe, or I do it manually. So saying that, why should anyone find 0 days, and why do I find the 0 days on the mainframe? And I guess the reason why you should find them is that if we don't find them and an attacker finds them first, this can have serious impacts for all the reasons why they would target a mainframe. We want to be the ones who find it first and report it to IBM or whatever vendor first. Then also just on a practical perspective on, for example, like a pen test, if we wanted to, let's say a company was running an out-of-date binary, because we don't have access to the IBM security portal, and to get access to it, you need to sign a lot of legal. If we wouldn't know if someone was running out-of-date software, and we couldn't tell them unless we were the ones who found it. And also, and this is, I guess, my reason, it's fun, and if you like exploit dev, so. I guess I'll explain just, what privilege escalation just in the abstract means, and it's starting at some sort of privilege and gaining something higher. So the way we normally want to do this is we want to find a program that runs with a higher authority than what we already have, because there's no point taking over a program which runs with our authority already. We don't get anything from that. So we want to find that program, and then we want to mess with the inputs. The inputs can be, there might be data sets it reads in, it might be environment variables it has, it might be network sockets, it might be parameters. There's lots of different ways you can mess with the inputs. And so I guess the attack path for how I find mainframe exploits is, first you just find programs that are running APF authorized. These are programs that can run special assembly instructions, so that's the higher authority part. We then attempt to try and crash the binary or the application. And the reason why we want to crash it is because if it's crashed, we know it's handling our input weird. So that's a good sign, at least for us. Then we want to see that, OK, we've crashed a program. Why did it crash? Was there something that we override? Is there some pointer we've overwritten which was meant to point to somewhere important, but we've put some random stuff in there? And a pointer is just a little bit of memory that says, here's where some other memory is. So in case, yeah. We then want to see, OK, we can overwrite some important pointers. Let's execute some arbitrary code, because that's how we can then get into key 0, which I'll explain later. And after we're in key 0, we can become special. And if we're special, we can access anything on the mainframe, and that's bad. So why are we trying to get into key 0? What can we do with that? Well, there's a little bit of memory called the ACEE, and it just says privileges that your user has. And so you can read it from memory because it's readable. So anytime you run a program, let's say I'm the one who runs it, it'll be, this user is called Jake. He has not special authority, and he has not operations authority, something like that. And importantly, normal programs can't write to it because it's in key 0. And because if a program could write to it, it could just flip some bits that say, oh, this user's called Jake, but he does have special, and he does have operations. So if we can manage to get into key 0, we can write to it, and we can just tell the program that we're running with special authority. And this is the simplest target on a mainframe for privilege escalation. There's other methods, but just, for simplicity, we're just going to use this. So how do we get into key 0? We need to be running program as authorized code. And what makes something authorized code? It has to be found in an APF authorized data set. The flag has to be set to AC1. And once these two conditions are met, we can run modeset and get key 0. That's the special assembly instruction allows us to run. So how do we how do we leverage this mode set? So we first go into key 0 with SVC 107, that's mode set. We then load the ACI from memory, and this is we know where the ACI is in memory. We then flip the special bit here, and then when the program runs, we'll have special. So we just put this into a JCL, and we run the program, and so we run it here, and when this runs, after we run, we'll have special. And the problem with this is that this is like a known technique, and it's something you would actually check on an audit/pen test, where this is programmed, so if we could run any code we wanted to, we would compile this program into an APF authorized library, we'd give it we'd give it AC1, and we'd run the program. But to be honest, on most tests, you will not find that you have update or alter access to compile a program to an APF authorized library. So we need to think of another method for us to gain access. And so this is like someone talked about this at Black Hat a while ago. So we're going to assume that some bad developer who's not very good at security has compiled some vulnerable code. And if you're if you know anything about buffer overflows, you'll immediately know that this is vulnerable. But the reason why is because you've set the buffer to length 150. So when you run the program, it will put some space of 150 bytes that it will store it will reserve in memory. And then what gets does is it reads in from the input, and it will keep filling up that buffer until it will just keep filling up that buffer until it's the end of the input. And the reason why it's vulnerable is because if you give it 160 characters, it will overflow the buffer, and some important things might be overflown. And just this isn't like code that was found. This is just something I've just compiled, but there has been code that I found by IBM that basically did this, so not good. So how do we run the program normally? Well, it's a mainframe, so we have to do a batch job. So this is a JCL where we run that getEcho program, we give it input and our sysin, and this just has, so this is a data set here, and in this data set, we've put just the text Jake, and so we run the program, and it runs this load of output from a JCL. This is what would be printed from like a line printer back in the day, and so it runs it. Hi, what's your name? Reads the Jake from the input and puts that into the buffer and writes that out. So good day, Jake. So first thing that any type of exploit dev that you do is you take the binary that you're trying to test and you run it through some static analysis. And for this, we're going to be using amblist. Amblist just takes the module you're trying to run, and it will list some flags that are set, and it will also list some symbols. So one of the flags that's important to notice is that APF code 000001, that means it's AC1. So that means that if this runs in an APF authorized data set, it will be authorized. And the next thing is that if we didn't know that the program uses gets, we could see that, oh yeah, at 3BO, the symbol gets is used. And so one of the things that I just did to find the lowest hanging fruit on a mainframe to find some 0 days was I made just a script that just ran through and amblisted every single APF authorized code, checked to see if it was AC1, and then also checked if gets was there, and there was, so not good. So once we've did some static analysis, we want to debug the program and find out, what is it actually doing, where is it using gets, because maybe it uses gets, but it's on some input that's actually we don't actually it doesn't actually run with code we can control, but it does. We use the program called TSO Test, and it is a debugger that's been around since the 1970s, so it's very not user-friendly, much less than GDB. And so the way it works is you can set breakpoints, you can go to breakpoints. So at the moment I've said at 3BO, go. You can list where you are in memory with where. You can list various registers, and you can list memory at those registers. I'll explain why I've chosen these registers in the next couple slides. But yeah, there's the other thing is if you're running it in a JCL, it's not like an interactive process. You run it, and then you look at the output afterwards. But yeah. So we run it, and we run our debugging thing, and then we look at our spool, the output here, and we can see that it's stopped at gets, so we do know it's actually running the gets program. And we've listed register 1 and register 13 and the contents at those registers. And the reason why is that register 13 is the pointer to our DSA. A DSA in Unix Windows term can be loosely thought of like a stack frame, and a stack frame is basically all the memory that your program, your one function will need while it's running. So gets will have its own stack frame. The main program will have its own stack frame. So at this point, when we've stopped at 3BO, the gets program, the gets function hasn't run yet. And so what we have is that at register 13, we have the pointer to call our DSA. We can see the next available byte pointer. This points to where some free memory is. So the reason why this is important is that when the gets function actually does run, it will look at that next available byte and make the gets DSA there. And importantly, we can look at register 1, which shows us our parameter list, and that will point towards our buffer, which is gets only has one parameter, which is the buffer. And another thing that's important to note is that the buffer is before our free memory, which will be important once we create the gets DSA, because here's it straight after the gets creates its stack frame. The most important thing that we can find here is that this previous pointer is pointing back to the start of our cooling DSA, and our buffer is before that. So if we can manage to make a buffer that's large enough to overflow that into that previous pointer, we'll be able to muck with the execution of the program. And hopefully if we can do that, then we can get code execution. So the first thing to do is let's see if we can crash the program. And so the way we do this is we make a really large input, and it doesn't really matter what you really put in it. I think on Unix or Windows, you'll use A's. On a mainframe, it's nice to use 4-character words because of storage alignment, so that's what I've chosen to do. And I've also chosen things which are very unlikely to appear on actually in like a system dump. So if I know these appear in memory, if I see these appear in memory in important places, I know it was me who put them there. And so this is called an egg hunter in like other places. And we can also put the last 4 characters as something different, so we can work out that we've got exactly the amount we needed to overflow the previous pointer, because that's what we really want to go for. So we end it with Kale. It could be anything, doesn't really matter. So we run the program, and we look in register 13, and we see that Kale is now there. If anyone's like, that doesn't look like Kale, I know ASCII, that's not it. Mainframes have their own encoding called epsidic, and so D2, C1, D3, C5 in register 13 there is Kale. So why has it crashed? What has it tried to do? And this is what it's tried to do. So you can now see that previous pointer has now been replaced with Kale. And so what the program will do is once it's finished with the gets function, it will try to load back that previous cooler DSA, and it will look at that previous pointer and go, okay, I need to load it from Kale. It tries to load some memory from Kale. That's not a real address. It doesn't know what to do with it, so it just crashes. How do we leverage this to get privilege escalation on a mainframe? So first step is we want to point that previous DSA, which we had as Kale before, towards the start of our buffer, because we control that. Then inside that buffer, we make a fake DSA, so it thinks that it's loaded some actual memory. But in that cooler DSA, there is a register 14, which is the return address. So if we can control the return address, we can get code execution by just pointing that towards our buffer, towards some other part of our buffer. And going back to that previous one of the previous slides where we showed that what we would run if we could write to a APF authorized library, we're going to be compiling that program, copying the binary from there, and then putting that into our buffer so that we can make that program run. And when that program runs, we will flip that special bit, and we will become, we'll have access to everything. So here is what the final storage of the memory will look like as we're trying to, when we put in the actual code that will give us access, which will flip our special bit. And so we have that previous pointer there. It's now pointing back to the buffer here. It will then fill it up with the return address. The return address then points to our shellcode. That shellcode will run, and we'll have special. So, yay. So I guess kind of like the conclusion is that currently no one is really looking at these APF mainframe vulnerabilities. They're auditors, just it's not in their purview to look at. Pen testers, they don't know how, and then until 6 months ago, I also didn't know how, so I was one of them. But I guess one of the things I've heard is that, okay, people will learn how to, they might find a vulnerability on a mainframe, but they'll never have the mainframe knowledge to work out how to exploit it. This is fairly untrue. There's all the documentation, and I think I had an intern who I taught up how to do this type of stuff in like a month or two. So it's not impossible to learn. Also, just the fact that these types of programs and vulnerabilities could be present in some of the most important data, like banks, telecoms, insurance, retail. It'd be bad if some of these mainframes got hacked. The fact that I've been able to find, personally, a good number of 0 days is, I guess, maybe I'm the only one who can find them, and yeah, but maybe not. So probably we should have some stuff on that. And also, one thing that is kind of a little bit frustrating is, so if you talk to a mainframer, they'll say buffer overflow is not possible on a mainframe because of storage keys. It's not. If it's running in an authorized code, we can change our key. But they also know the term storage overlay, which it basically means the same thing, but I guess they just don't. It's not. Yeah. So if I talk to a mainframer, I'll call it APF authorized storage overlays, and then it's like, oh, okay, yeah, I guess that could be possible. So that's one thing that I guess I've learned.